Another day, another story. Ozone, a colorless gas, plays a significant role in the atmosphere. While it shields the Earth from the sun's harmful ultraviolet rays in the stratosphere, it becomes a harmful air pollutant closer to the ground, leading to health issues such as chest pain and breathing difficulties. In the upper troposphere, where most aircraft operate, ozone acts as a potent greenhouse gas, contributing to global warming. Despite efforts to reduce its sources, there are indications that human activities continue to drive an increase in upper tropospheric ozone. Welcome to Tabo Eminent Channel. Recent research from MIT confirms a clear human influence on the increasing ozone levels in the upper troposphere, based on a 17-year satellite record. This finding underscores the urgent need for action to address the impact of human activities on our atmosphere. We confirm that there's a clear and increasing trend in upper tropospheric ozone in the northern mid-latitudes due to human beings rather than climate noise, says study lead author Xinyuan Wu. Now we can do more detective work and try to understand what specific human activities are leading to this ozone trend, adds co-author Eileen Fiore. Understanding the causes and impact of ozone is a complex task. Ozone is not directly emitted but is a result of precursors, initial components such as nitrogen oxides and volatile organic compounds, VOCs, that react in the presence of sunlight to create ozone. These precursors are produced by vehicle exhaust, power plants, chemical solvents, industrial processes, aircraft emissions, and other human activities. The duration and presence of ozone in the atmosphere are influenced by various factors, including the type and scale of human activities in a particular area, as well as natural climate variability. For example, a strong El Niño year could alter the atmospheric circulation in a way that impacts ozone concentrations, independent of human contributions to the atmosphere that year. It can be quite challenging to distinguish between human-induced and climate-driven factors contributing to ozone trends, especially in the upper troposphere. Adding to the complexity is the observation that lower tropospheric ozone, closest to ground level, has plateaued and even decreased in certain regions at northern mid-latitudes over the past few decades. This decline is primarily attributed to the concerted efforts in North America and Europe aimed at curbing industrial sources of air pollution. Near the surface, ozone has been observed to decrease in some regions, and its variations are more closely linked to human emissions, Wu notes. In the upper troposphere, the ozone trends are less well monitored but seem to decouple with those near the surface, and ozone is more easily influenced by climate variability. So, we don't know whether and how much of that increase in observed ozone in the upper troposphere is attributed to humans. Wu and Fiore sought to determine if human activities could leave a distinct fingerprint in ozone levels, noticeable through satellite observations in the upper troposphere. In order to identify this signal, the researchers needed to establish what to search for. To achieve this, they turned to simulations of Earth's climate and atmospheric chemistry. By using methods developed in climate science, they hypothesized that if they could simulate numerous potential climate variations over recent decades, all with the same human-generated sources of ozone precursor emissions but each starting with slightly different climate conditions, then any disparities among these scenarios ought to be attributed to climate noise. Consequently, any common signal that emerged when averaging over the simulated scenarios should be linked to human-driven causes. This distinctive signal would serve as a recognizable fingerprint of human-induced ozone, which the team could then seek in real satellite observations. The team utilized a cutting-edge chemistry climate model to conduct simulations with various climate scenarios spanning from 1950 to 2014. Their findings revealed a consistent signal across scenarios, identified as a human fingerprint. In order to delve deeper, they analyzed tropospheric ozone products obtained from multiple instruments aboard NASA's Aura satellite. Quite honestly, I thought the satellite data were just going to be too noisy, Fiore admits. I didn't expect that the pattern would be robust enough. The team utilized satellite data to examine upper tropospheric ozone levels from 2005 to 2021 and confirmed the presence of human-caused ozone as predicted by their simulations. This human-caused ozone signal is particularly prominent in Asia, where increased industrial activity and environmental factors have led to the transport of pollution, including ozone and its precursors, to the upper troposphere. Wu and Fiore are now focused on pinpointing the specific human activities responsible for the rise in upper tropospheric ozone. Where is this increasing trend coming from? Is it the near-surface emissions from combusting fossil fuels in vehicle engines and power plants? Is it the aircraft that are flying in the upper troposphere? Is it the influence of wildland fires? Or some combination of all of the above? Fiore says, being able to separate human-caused impacts from natural climate variations can help to inform strategies to address climate change and air pollution. The increase in ozone levels in the upper troposphere is largely attributed to human activities. This phenomenon is primarily due to emissions from industrial processes, vehicle exhaust, and other sources of pollution. Here are some key points explaining the link between human activities and increased ozone in the upper troposphere. Emissions of ozone precursors. Human activities release large amounts of ozone precursors, such as nitrogen oxides, NOx, and volatile organic compounds, VOCs, into the atmosphere. These precursors undergo photochemical reactions in the presence of sunlight, leading to the formation of ozone. Transportation and industry. The combustion of fossil fuels in vehicles, power plants, and industrial processes is a major source of NOx and VOCs. As these pollutants are emitted, they can be transported to higher altitudes, contributing to the increase in ozone in the upper troposphere. Stratosphere-troposphere exchange. Changes in atmospheric circulation patterns due to climate change can enhance the exchange of ozone between the stratosphere and troposphere. Human-induced climate change may be altering these patterns, leading to an increase in tropospheric ozone. Biomass burning. Human activities such as deforestation and agricultural burning release large amounts of pollutants, including NOx and VOCs, which contribute to ozone formation. These activities are particularly prevalent in certain regions, exacerbating the problem. Air travel. Aviation emissions, particularly from high-altitude flights, contribute directly to the increase in ozone in the upper troposphere. Aircraft engines emit NOx, which can lead to ozone formation at cruising altitudes. The science behind ozone formation. Ozone, O3, is a gas that exists in both the stratosphere and the troposphere. In the stratosphere, ozone forms the ozone layer, which protects life on Earth from harmful ultraviolet, UV, radiation. However, in the troposphere, ozone is considered a pollutant and has adverse effects on health and the environment. The increase in tropospheric ozone is a concern because it is a potent greenhouse gas and can contribute to global warming. Additionally, it has harmful effects on human health, vegetation, and ecosystems. Addressing the issue requires reducing emissions of ozone precursors through cleaner technologies, stricter regulations, and international cooperation. Thanks for watching. Request you to subscribe the channel.